All right, so here's an example for something that's rolling down the ramp. We have a uniform ball of mass m equals 6 kilograms and radius r rolls smoothly from rest down a ramp at an angle of 30 degrees. The ball descends a vertical height h of 1.2 meters to reach the bottom of the ramp. What is the speed at the bottom? So we're given m is 6 kilograms. We're not given what the radius is, which is very interesting. And we're also given that this ramp is 30 degrees and the height of the ramp, h, is 1.2 meters. Now, whenever they give you a height like this, my mind automatically goes to conservation of energy, just because you have potential energy at the top, and then as it rolls down, you're going to get kinetic energy at the bottom, and we're looking for speed at the bottom. So that's usually the easiest way to get velocity or speed at the bottom of an incline. So that's what I'm going to do. Now, the hard part here is to remember that because we're rolling down a ramp, at the bottom of this incline, we don't have just translational kinetic energy, we also have rotational kinetic energy. Okay, so you have to have two equations for kinetic energy at the bottom. So we have, for conservation of energy, we have energy initial equals energy final. All of our energy initial, of course, is potential energy because we're at a zero velocity at the top. So we have potential energy initial equals, and then as this goes down, it not only translates, but also rotates as it's going down the ramp. So that's going to turn into both kinetic energy final translational plus kinetic energy final rotational. Okay, so what we get here when we plug in our equations is mass times acceleration of gravity times height equals 1/2 mass times velocity final squared, this is height initial, plus 1/2 our rotational inertia times angular velocity squared, and this is angular velocity final, of course. Okay, so they also give it to us that it's a uniform ball. So since it's a uniform ball, I'm guessing that we're going to be using the rotational inertia for a sphere. It doesn't specifically tell us that, but if I remember correctly, in the book we use rotational inertia for a sphere because it's a uniform ball. So that rotational inertia for a sphere, I of a sphere, is equal to 2/5 mr squared. You can look that up in the book. That's one of the ones that I want you guys to memorize as well. So that's going to go in for our I. And then also, since we're finding the final speed at the bottom or the final velocity at the bottom, I'm also going to use how we relate linear and rotational speed, our velocities, right? Our linear velocity and our angular velocity. So we get omega equals v over r for that. So I'm going to be plugging that in for omega right here. So we get mgh initial equals 1/2 mass times velocity final squared plus 1/2 times 2/5 mr squared, and then this ends up being v squared over r squared. So you can see why they don't give us a radius here is because the radius cancels out. So we get r squared here, cancels out with the r squared there. And then so simplifying, also we can see that there's a mass in every term, so all the masses are going to cancel out as well. So we end up getting gh initial equals 1/2 v final squared plus 1/2 times 2/5 is 1/5 times v squared. So now just simplifying more, we know the height, we know the acceleration of gravity, and then if we make these fractions into our least common denominator and then add them together, we get probably 10 as our least common denominator. So we end up getting 5/10 plus 2/10, which is 7/10. So we get gh initial equals 7/10 v final squared. Solving for v final here, we get 10 gh initial divided by 7, take the square root. Plugging in our numbers here, we get 10 times 9.8 meters per second squared times the height initial, which was 1.2, meters divided by 7. So here, well, my calculator's in the other room, so I need to use my phone. So 10 times 9.8 times 1.2, and then divide by 7, I get 16.8, and then I'm going to take the square root of that, and I end up getting 4.1-ish for my V final, 4.1 meters per second. So that's my final velocity for this object at the bottom of the incline. Now for part B, it says, what are the magnitude and direction of the frictional force on the ball as it rolls down the ramp? So frictional force, if we draw a picture of what's happening here, here's my ramp and here's my ball as it rolls down. Now the frictional force is going to be up the ramp like this. The way you need to think about this is what would happen if there was no friction. If there was no friction, like this ramp was made of ice or something like that, it would just slide right down the ramp. So because it doesn't just slide right down, there has to be something here catching it and causing it to rotate like this. So the tendency of this bottom right here is to slide right down, so friction has to be in the opposite direction, which is why the friction force here is up the ramp like that. So force of friction is right there. Now this friction force is what causes the torque on this object to then cause it to rotate. So we have our moment arm, which is the radius of the object, and then we have our friction, which is the force that causes the torque. So of course we know torque is equal to moment arm, which is the radius, times the force, which is the force of friction, and then the angle between these two things right here is 90 degrees. So sine of 90 degrees ends up being just 1. So that whole term we don't even really have to write down if we remember that when we have a perpendicular force to the moment arm, then we have our maximum torque. Okay, so we can just write that RF of friction. Now we also know that torque is also equal to our rotational inertia I times angular acceleration here. So we can set these two things equal to each other. So we get R times the force of friction equals rotational inertia times angular acceleration. And of course, again, rotational inertia here is for a sphere, which is 2/5 mr squared. And then for angular acceleration, I'm going to plug in relating that to linear acceleration, acceleration over R. Now, the reason I'm going to do this is because in the previous video, we derived an expression for acceleration that I'm going to use to find that acceleration here. It's just a little shortcut. You can also just use Newton's second law in order to find our acceleration. And it also uses this equation here because really what we're solving for, remember, in part B, is what is the magnitude and direction of the frictional force on the ball. So you can use Newton's second law if you want to. We can also use kinematics, things like that, in order to find an acceleration down the ramp. But we don't yet know what the acceleration is, so I'm going to use that equation that I derived in the last video. So what we end up getting is R times the force of friction equals 2/5 mr squared times my angular acceleration, which is A over R. So R cancels with this R, this radius cancels with this radius, and I end up getting my force of friction equals 2/5 m times A. Now I know my mass, but I don't know my linear acceleration yet, or the acceleration of the center of mass. So like I said, we can use that equation that we derived in the last video, which is also on page 300. Acceleration is equal to g times the sine of theta, where this theta is the angle of the ramp, over 1 plus I over mr squared. So now what we do is we plug in I, so our rotational inertia, we get acceleration equals g sine theta over 1 plus 2/5 mr squared over mr squared. Those mr squareds cancel out, and so this becomes g sine theta over 1 plus 2/5. okay? Now, plugging in numbers here, and then the bottom, also, we want to make sure that we have a better expression on that denominator there. So obviously 1 is 5 over 5, and then we add 2 over 5, which is 7/5. So we end up getting acceleration equals g, which is 9.8 meters per second squared, times the sine of the angle, which the angle of the ramp was 30 degrees, over 7/5, which if we are dividing by 7/5, really what we're doing is multiplying by 5/7. So I'm going to multiply this whole thing by 5 and then just divide by 7 here just to make it a little cleaner. So here we end up getting an acceleration of, and again, I'm using my phone as my calculator because my calculator's in the other room. So sine of 30, and then I'm multiplying that by 9.8 times 5, and then dividing that by 7, and I end up getting an acceleration of 3.5 meters per second squared. Now, of course, this is down the ramp here, okay? So down the ramp, I get an acceleration of 3.5 meters per second. So I'm going to plug that in for my acceleration up here, but of course, I know that the force of friction is up the ramp. So if you remember in the last video, I described how this equation right here is, in the book when they derive it, they have a negative sign right here. And it's because that's down the ramp. They're calling that the negative direction. So when I plug it into my equation, if I can plug in a negative 3.5 here because it is down the ramp, but of course I will get a negative force of friction. Here, I just want you guys to remember what direction the force of friction is, what direction the acceleration is. So if I plug in a positive 3.5, really what I'm getting is the magnitude of the force of friction, and then I just have to remember which direction is which, right? Which direction my force of friction is in, what direction my acceleration is in. So I end up getting 2/5 times m, which they give me is 6 kilograms, times acceleration, which I just found to be 3.5 meters per second squared. And so force of friction ends up being, finally, times 2 divided by 5, 8.4 newtons. And I know that my direction for this force of friction is up the ramp because that is what causes it to then rotate in the direction that it does.